Hello and welcome back to our discussion series of this course. Now, I remind you that last time what we discussed in the cutting tools and types of machining, that what is oblique cutting, what is orthogonal cutting, and I told you that normally in practice oblique cutting is used in practice, okay, normally, because in oblique cutting the tool grabs the workpiece material gradually, and therefore, the tool strength, available tool strength will be more than in case of the orthogonal cutting. Okay. Now, orthogonal cutting is a two dimensional cutting where the chip flows exactly perpendicular to the cutting edge, okay, because in case of orthogonal cutting the tool edge is perpendicular to the cutting velocity vector, and in case of oblique cutting this is not the case, that means the tool edge is inclined with respect to the cutting velocity vector, and therefore, the chip flows along the XYZ axis on all the all these axes. So, as a result what happens is that the cutting forces in case of orthogonal cutting, if the cutting forces remain in one plane, XZ plane, in that case in the oblique cutting the cutting forces will remain in XYZ, because it is inclined, okay? The cutting edge is inclined with respect to the cutting velocity vector. So, that is the basic difference between the oblique cutting and the orthogonal cutting, all right. So, once again mostly it is the oblique cutting that is in practice. Next we discuss the type of chips, and I told you that there are continuous chips, there are discontinuous chips, and there are continuous chips with a built up edge formation. I told you about the mechanism of the built up edge formation, that why built up edge is formed. Once again, because of the high strain rate of deformation, because of the very high pressure and temperature, a thin layer is removed from the chip, okay, which is in contact with the rake face of the tool, and as a result of that high pressure and the temperature, a thin layer will also be removed from the rake face of the tool. So, those two surfaces become nascent surfaces, that is fresh surfaces, and they will have the ability to get welded. So, they get welded, and the welded junction between the chip, nascent surface of the chip and the nascent surface of the rake face, this welded junction will resist the flow of the chip along the rake face, and it will start piling up at the on the rake face. So, particularly around the tool edge, cutting tool edge, all right. So, once it is piling up, it will further create the resistance to the flow of the chip, and the piling up will start growing, and as it grows beyond a certain level, so it becomes unstable, and then it actually breaks, but then the condition remains the same of the high pressure and the high temperature. If it remains the same, in that case the piling will continue, and the built up edge will again start growing, again getting piled up, and then it will be broken because it is unstable, and then again piled up, and so on, it will continue. Now, we said that this piling up happens because there is a certain temperature and pressure. So, that temperature and pressure occurs at a certain cutting condition. Particularly, I mentioned that for the high speed steel and the mild steel as a workpiece and high speed steel as the tool. So, this combination, for this combination of the workpiece and the tool, the cutting velocity is normally in the range of 80 to 110 meter per minute. Okay. So, now if the velocity becomes more than 110 meter per minute in case of mild steel and the high speed steel, then the temperature that will be occurring will be more than the temperature of recrystallization of the metal, okay, the workpiece material. And what is recrystallization? I told you in the discussion of the materials and their properties, that the new grains are formed. So, in that case the built up edge vanishes, because the temperature goes beyond the temperature of recrystallization. Okay. So, that means the formation of the built up edge becomes only at a certain range of cutting parameters, particularly the cutting speed. Okay. And when the temperature occurs within a certain level. Now, built up edge involves therefore welding and rupture of the chip material. Okay. So, welding, because the two nascent surfaces of the chip and the rake face, they are getting welded and it will be ruptured, okay, of the chip material. So, welding is affected by the temperature and the normal pressure near the tool tip, which becomes very high, and the rupture is influenced by the strain hardening process, as I said, and the thermal softening of the chip material, because at a high temperature it is thermally softened, all right. And the temperature which actually occurs as you increase the cutting velocity, it is in this way, that the temperature remains is proportional to the square root of the cutting velocity. Okay. So, as the cutting velocity is increasing, then the temperature will increase, but in this fashion. So, it will be non-linear, it will not be linearly, not proportionally increasing, but it will be like this, because it is V c to the power 0.5. Okay. This is proportional to V c to the power 0.5. So, once again, so at this temperature it will be welded, since the temperature is increasing, cutting speed is increasing, and then it will be ruptured. So, therefore, the welding is affected by the temperature and the normal pressure near the tool tip, which is very high. But the rupture once again is influenced by the strain hardening and the thermal softening of the chip material. Now, let us see what happens now that we know that what is continuous chip, what is discontinuous chip, what is continuous chip with the built up edge formation. Let us see what happens as the cutting speed increases. Let us say for different condition of machining, the cutting speeds are different. Okay. So, for different cutting speeds, what will happen with the surface roughness or the surface finish? As you understand that 1 by surface roughness is surface finish, meaning the more the surface roughness, rougher is the surface, surface finish is low, okay, and vice versa. If the undulations or the surface roughness, by undulation I mean to say that if we look at the surface, so if you suppose exaggerate the surface, it can actually look like this, all right. So, let us say this is the metal surface. So, if you exaggerate, this will be the undulation, okay. So, more the undulations, more will be the roughness and less will be the surface finish. But if a surface looks like, for example, like this, that means the undulations are less and the surface finish is better. So, of course, you know that, I mean, you can say that this surface is finish of this surface is better than this surface, because here the surface roughness is more than in this case. So, let us see what happens here. Now, as the cutting speed increases, the curve which represents the change in the surface roughness goes like this. Okay. It actually has 3 distinct zones. One zone where it is actually coming down, then it starts improving, surface roughness is going up, okay, and then surface roughness going down. So, that means what happens, let us say from the very beginning, here when the cutting speed is small, let us see, okay, the small low cutting speed. So, with the low cutting speed, the discontinuous chips happen. Okay. Discontinuous chips means I already told you that there will be fluctuation in the forces and there will be feed marks remaining on the surface, spoiling the surface. So, the surface finish will be bad. So, therefore, the surface roughness is high. Okay. Then as the cutting speed increases further, let us say beyond this point, then the chip becomes from the discontinuous to continuous chip, because the speed is increasing, and therefore, the surface finish improves, meaning the surface roughness decreases, all right. So, it comes to this point, then it goes into that zone of the cutting speed where the temperature and pressure will be favorable for the built up edge formation, Okay. Let us say mild steel, I remind you that this is 80 to 110 meter per minute. If it is a mild steel curve, in that case this will be the 80 to 110 meter per minute cutting speed, and then since the built up edge forms, then the surface finish will be bad, because the again cutting force fluctuates, then the the power fluctuates. As I said, the rake angle changes, and it is a dynamic change in the rake angle as the built up edge piles up and then it breaks. So, therefore, the surface finish is deteriorated, and the surface rough, because the surface roughness goes up, it goes up to a point beyond which of the cutting speed the temperature rises further, because it rises like to the power root over Vc. Okay. Then from here the temperature will be more than the temperature of recrystallization, and the built up edge vanishes. Therefore, what happens is the surface finish improves, and the surface, because the surface roughness goes down, okay, because the built up edge is no more and the cutting process is smooth. So, these are the three distinct zones that are demonstrated during the cutting process if the for different cutting velocities. At lower cutting speed is discontinuous, at medium cutting speed it is a built up edge can be formed, at higher cutting speed the surface finish is better. Okay. So, surface finish overall will be always better at a higher cutting speed than at the lower cutting speed. Okay. And at this moment what we are telling is the reason is the built up edge does not appear for this higher cutting speed. There are other reasons as well, we will discuss it later. Okay, here you can read it, it is written here that the zone 1 is the discontinuous chip, initially poor surface finish, it improves at speed increases, and the chip becomes semi discontinuous here. So, zone 2 it comes in, I already told you, built up edge is formed, continue till the recrystallization temperature is reached, and then the continuous chip without the BUE, because BUE vanishes since the temperature goes beyond the temperature of recrystallization. Okay. Next that we will discuss, the next topic, what is tool nomenclature, is that how the tool angles and the geometrical parameters of the tool, particularly the angles and the tool nose radius, how they are defined. So, in different countries this nomenclature or the definition of the angles it is different, all right. So, depending on that we have distinguished, particularly I will discuss it 3 systems quickly, and one of them is used in India, but all others used in other countries, but we have to discuss because we have to understand since we are using that tool in that nomenclature, in that system, where the nomenclature is given in that system. So, we have to use those tools in our system. So, we have to adjust accordingly. How to adjust, what are those adjustments, we will see it now. So, the first nomenclature is in the coordinate system. This is expressed in the coordinate system, where the coordinate x, y, z coordinates are used. Okay. So, let us say this is the plane, which is the base plane. Base plane is the plane where the tool is rested, okay, like that. Now, with respect to the base plane, there are 2 perpendicular planes. One is the transverse plane, this is along the transverse feed. So, transverse feed, I will remind you that that is the feed I described, that when it goes, the tool moves perpendicular to the cutting, perpendicular to the axis of the workpiece, okay, where facing operation is done. So, that is the transverse plane along the transverse feed. Okay. And another plane perpendicular to both the base plane and the transverse plane is the longitudinal plane. Okay. Here it is given Px. So, this Px, that is the longitudinal plane, is along the longitudinal feed. Okay. Longitudinal feed is the normal feed direction. All right. This is the direction along the axis of the workpiece. Okay. So, these are the 3 mutually perpendicular planes in which the angles, tool angles are defined. Okay. So, look in here, This is the tool in the base plane, that is the PR plane, that is base plane. Now, at this point B, we will take two sections. One section is XX, all right. This is along the longitudinal feed direction here, and another section, this is the YY, YAY or YY. This is along the transverse plane, okay, YY. Now, we will place these views here, that is XX we will place it in here, and YY cross section, how you can see that cross section, we will place it here, all right. Now, if we see that, if we take the cross section at this point and look at the tool will be visible in this way, all right, where this is the rake face, this is the flank face. Mind one thing here, in this base plane, rake face and the flank face will not be visible. Okay. So, in this case what happens is that you take the plane, you take the cross section like this, and then you place it like this and see this, okay. Or you take this cross section like this at B point and then you place it here. So, you look at this, all right. Then only the rake face and the flank face will be visible. Similarly, for the YY, if you cut it like this, all right, and reveal that what is visible like this. So, in this plane, okay, rake face here and the flank face will be visible. Otherwise, in this base plane, the neither rake face nor the flank face will be visible. So, now all the planes are there, 3 planes here. So, in here the angles, they are given as the back rake here, this is the one of the rake angles. Now, mind it, there will be 2 rake angles, because there are 2 inclinations along the rake face, all right. 2 inclination, because one is along which the tool moves, chip flows, and another inclination where the flow to the chip will be, resistance to the flow to the chip will be minimum, okay, or the rake angle is more. So, therefore, there are more than one rake angle. Now, here this is another inclination of the rake angle, and this is given by the side rake angle. So, both the rake angles define the inclination of the rake face with respect to a line perpendicular to the cutting velocity vector. Okay. So, for example, in case of the back rake angle, this is the angle between the rake face here and a line, this is the line which is perpendicular to the cutting velocity vector. Okay. Similarly, here this is the line XA, this is perpendicular to the cutting velocity vector, and this is the angle between that line and the rake face of the tool. So, these are the 2 rake faces. Similarly, there will be 2 flank faces. Since there are 2 rake faces, there have to be 2 flank faces as well. So, one flank face is the end flank angle delta E, and another is the side flank angle. So, this is the delta S. So, this is the 2 sets of angles, 2 rake angles and 2 flank angles in the coordinate system, and coordinate system is also called the American system, because it is used in the United States. Okay. Now, other 2 angles are the cutting edge angles. These are the 2 cutting edges. This is the principal cutting edge and this is the auxiliary cutting edge. So, the principal cutting edge makes an angle with the x axis, all right, rather with the y axis, let us say, in this y axis, which is called the side cutting edge angle. And when the angle is with respect to x axis, this is the end cutting edge angle with the auxiliary cutting edge. So, once again, principal cutting edge and y axis make the angle of the side cutting edge angle, and the auxiliary cutting edge and x axis make an angle of end cutting edge angle. So, this is another set of angles, that is cutting edge angles. So, 3 sets of angles, 3 sets of rake, flank and the cutting edge angles. So, there are 6 angles altogether, and another important parameter is the nose radius. So, So, this is the R. So, normally what happens is the tool is not very sharp, because when the tool is sharp, let us say like this, in this case there will be lot of stress concentration, okay, and the tool may be broken and it can actually chip in. So, that is the chipping of the tool. So, it can actually break as soon as it comes in contact with the workpiece. So, therefore, normally there is a nose radius given to the tool tip, and we will see later on that it has another advantage also, that when we have the nose radius, the surface finish improves. Okay. I will tell you the physics behind it, why the surface finish improves, when we discuss the surface finish chapter. All right. So, overall there is a nose radius given, and the value of the nose radius can be different, all right, and that nose radius is also mentioned in this nomenclature as one of the parameters. So, 6 angles and the nose radius. So, these are the 7 parameters which are mentioned in a certain sequence. So, in the particularly coordinate system, that sequence is, first angle will be the back rake angle, then the side rake angle, then the end flank angle, side flank angle, okay, the end cutting edge angle and the side cutting edge angle. After that, this is a nose radius. Now, another thing is the flank angle and the clearance angle is the same. In some books you will find that it is given as a flank angle, in some books it will be given as a clearance angle. Okay. These are the same thing. Now, in the tool, when you are purchasing a tool, this will not be written, that which one is the back rake, which one is the side rake and so on. Suppose the tool may have this kind of a nomenclature, 4 degree, 6 degree, 8, okay, 9, 12, 13, and here it is 0.02, this is in inch, because it is American system. So, this nose radius is given in inch, but inch will not be written, it will be 0.02. So, you have to read, you will not be said that this will be back rake angle, you have to read that the first angle is the back rake angle. So, the back rake angle for this tool of this nomenclature will be 4 degree, side rake angle will be 6 degree, end flank angle will be 8 degree, side flank angle will be 9 degree, side flank angle is here, okay, it is like that, and so on. So, end cutting edge angle is 12, side cutting is 13 and the nose radius is 0.02 inch. So, this is about the coordinate system. As you can understand that this coordinate system is the easiest one, because it is in the x, y, z, all right. If the coordinates or the planes which are taken, like as I shown it here, if these planes are otherwise, in that case the figures may be, or the angles, definition of the angles may be little more complicated. Okay. Let us see another system which is called the continental or orthogonal rake system. Okay. This is the ORS, this is the orthogonal rake system. In the orthogonal rake system, the reference planes are the following, that it is the same base plane that in case of that we have taken in case of the coordinate system, where the tool is located, tool is lying there, all right. Now, with respect to that, we will take the other angles in other different planes. Okay. Now, with respect to the base plane, we have 2 more planes which are different than in case of the coordinate system. One plane which is the cutting plane, okay. This cutting plane is the PC. Cutting plane is the plane which will contain the cutting edge, okay, which will not go cut the cutting plane, it will contain, it will have the cutting edge. Cutting edge is lying on the cutting plane, that is the cutting plane containing the cutting edge. Now, perpendicular to that is an orthogonal plane. Okay. Orthogonal plane is actually perpendicular to this. Okay. Now, therefore, if we have the plane, if we have the view tool in the base plane like this, at this point B, we will take such kind of sections. One section which will be CC. So, this will be actually view because it is not a sectional view, it is not cutting, it is just lying on that C, because we said that the cutting plane will contain the cutting edge. This is the principal cutting edge, all right. This is the auxiliary cutting edge. Therefore, we said that these are the cutting edge angles. This is the principal cutting edge, this is the auxiliary cutting edge, all right. Now, with respect to this OO, so first let us say CC. CC is the plane which will contain the cutting edge. So, we will take a view because it is not the sectional section. Okay. So, the view will not be hatched. In this view, you understand that this will be, this is revealed actually like this. Okay. So, if this is the cutting edge, all right, principal cutting edge, this is the plane which is containing the principal cutting edge, then when it is showing it here, we will actually see the rake angle and the flank angle, or the rake face and the flank face, like in case of the coordinate system I explained. Okay. So, if we see the view, this, that is why it is written view CC, all right. This is the rake face, inclination of the rake face, and this is the flank face. So, this is the tool which is shown in the if we actually, that CC means that if we look at the tool from here perpendicular to this, right, from the top, if you see, I mean top in the sense that perpendicular to the principal cutting edge, you can actually see this view. So, in this view, this is the inclination of the rake face, and with respect to y0, this will be the angle which is called the tool inclination angle, which is I. All right. Now, this tool inclination angle is also called the angle of obliquity, that we will come little later. All right. I will explain it to you. Another section we will take as OO. All right. OO will be perpendicular to CC. Look at in here. Now, this is the orthogonal plane OO. OO is perpendicular to the PC, that is the cutting plane. Now, along this OO, if we see this view, all right, this will be the inclination of the rake face, and this will be the inclination of the flank face. All right. So, once again it will be principal cutting edge, we are cutting it like that, cutting it in the sense that we are say taking the sectional view along the OO, which is perpendicular to this edge, principal cutting edge, and we are looking it like this, what is in here. So, here it will be the flank face and the rake face that will be revealed here. All right. So, another plane we will take. Now, again here in this we will hatch it because this is the sectional view, okay. Whereas, in CC this was a view, and this view, as I said, this is like if you see the tool from here perpendicular to this. We will take another section which will be perpendicular to the auxiliary cutting edge. Okay. Perpendicular to the auxiliary cutting edge will be AA, and similar to this, all right, perpendicular to or similar to this, we will have a view like this. And in this view, if you see this in the auxiliary cutting edge, this is the inclination of the rake face. So, now I would like to point out one thing, that this inclination of the rake face and the inclination of the rake face here, or the inclination of the rake face here, they are different, okay, because I said there will be multiple or more than one inclination on the rake face. All right. So, in that, therefore, we are calling these rake angles which define the rake inclination of the rake face, they are differently, they are called differently. I will tell you what are those. Now, we have again three sets of angles, that is the one set of rake angle, one here, one here, one set of flank angles, one here, and one set of cutting edge angles. Here again this is the principal cutting edge, this is the auxiliary cutting edge, this is remaining the same in ASA or in ORS, whatever. All right. So, it is another set of angles, this is called the cutting edge angle, and this is tool radius, tool nose radius. Now, all these angles are given in a particular sequence, like in case of the ASA or the coordinate system, and this inclination is the this sequence is the following. First it is mentioned what is the inclination angle. Okay, inclination angle is here, this is the I. Next to that it is the orthogonal rake. Orthogonal rake it is called because this is the orthogonal plane. Okay, this is the orthogonal plane. All right, orthogonal plane is perpendicular to this, right, cutting edge. Therefore, these two angles I and alpha 0, it will be, these two angles will be sufficiently describe the inclination of the rake face. All right. So, in case, I mean, you can also say that there is a rake angle also. So, we do not show the rake angle in this rake angle in this system, ORS system, because I and alpha 0 inclination angle and the orthogonal rake angle together sufficiently clearly describe the inclination of the rake face. Similarly, inclination of the flank face will be defined by principal flank angle. You can see from here, principal flank angle is here, principal flank angle because this is the principal cutting edge. All right. So, on this edge, this is revealed, this plane it is revealed, and the plane is the orthogonal plane. So, both this orthogonal rake angle and the principal flank angle, they are in the orthogonal plane. All right. And the next is the auxiliary flank angle. Auxiliary flank angle is defined in the plane which is perpendicular to the auxiliary cutting edge. Auxiliary cutting edge is here P D, and perpendicular to that is the AA. All right. So, this is the auxiliary flank angle. So, these two angles, principal flank angle and auxiliary flank angle, they actually define the inclination of the flank face. And then we have the principal cutting edge angle. Principal cutting edge angle is with respect to the principal cutting edge and the x axis. Mind it, in ASA it was not principal cutting edge, it was the gamma s was the side cutting edge angle, and the side cutting edge angle was with respect to y axis, principal cutting edge and y axis, and here it is with the x axis. So, it will be 90 minus that angle, right, 90 minus gamma p is the gamma s. So, another angle is with respect to the auxiliary cutting edge and the x axis, this is called the auxiliary cutting edge angle. All right. So, these are the 6 angles like in case of the ASA, one set of rake angles, one set of flank angles and one set of cutting edge angles, plus one another parameter which is the tool nose radius, and since it is in the orthogonal rake system or it is also called the continental system, this is given in terms of in the unit of millimeter. Okay. Whereas, in case of coordinate system, since it is an American system, so there it is given in inch, that is the only difference. Okay. So, this is the sequence once again, in inclination angle, orthogonal rake angle, principal flank angle, auxiliary flank angle, auxiliary cutting edge angle, principal cutting edge angle and the nose radius. In this sequence, the numbers will be given, any values it will be given here. So, you have to read that the first value stands for the inclination angle, second value stands for the orthogonal rake angle and so on. All right. Now, by the way, this orthogonal rake system is the system which we adopt in India also, and some other countries like the European, some of the European countries including the Russia, Germany, probably France, I am not very sure, they use also the ORS system. In both of these systems, that is the ASA and the ORS, these angles which define the inclination of the rake face, inclination of the flank face or the inclination of the cutting edges, they are not sufficiently they do not coincide with the angles when the tool is in the working condition or when the tool has to be reground. Okay. What does it mean tool has to be reground is when the geometry of the tool is lost, okay, like it is worn out. So, the rake angle has to be established again, all right, because it is spoiled, it has been rubbed off. So, it is by the chip, okay. So, the wearing action has taken place, or the rake face or the flank face has been worn out. So, the tool, when it is reground, the tool has to be placed on the grinding machine according to the angle at which the tool will be working, okay, working angle we call it. So, those working angles, they do not coincide exactly with these angles which define the inclination of the rake, flank and the edge angles. Here is another system which is called the international or normal rake system. Okay. This is called the international system because many countries we are now trying to adopt one system where all the countries will have the nomenclature according to this system, so that it could be easier for all the countries to buy tools from each other and not have to bother about the angles which are working angles, okay, because on those working angles only the NRS will define the inclination of the rake face, inclination of the flank face or the inclination of the cutting edges. Okay. Let us see what are the planes that the NRS or the normal rake system uses. So, here we have the base plane which is the same as in case of the ASA or the ORS. Okay. Then we have the cutting plane. Cutting plane is the same as in the case of the ORS. Cutting plane will once again contain the cutting edge, principal cutting edge. Okay. Only here difference is that another plane is taken which is different from the orthogonal plane. Here it is called the normal plane, and the normal plane is perpendicular to the cutting edge. So, in other way, here what happens is that this cutting edge, okay, and this cutting edge which comes when we are taking the views here, on these cutting edges you take a normal, then you will get the normal plane. Whereas, in the orthogonal plane it is not the case, because orthogonal plane was inclined or perpendicular to the base plane and the mutually perpendicular planes. All those three will wear the mutually perpendicular plane. So, the normal plane is different than the orthogonal plane that we have taken in the ORS. All right. Okay. So, in this case CC, this is the view, all right. This is along the containing the cutting edge, and the view will be the same as in case of the ORS. We have taken this view along the CC, the same here. Then we will take another view, and this will be II along the auxiliary cutting edge. Okay. And here the view will be like this. So, this is the rake face, this is the flank face, all right. So, what we are having is the cutting edge. You understand that the cutting edge will be containing the rake face will contain the cutting edge, right. The cutting edge will be at the end of the rake face, is not it. So, therefore, this is the cutting edge and this is the cutting edge here, as you see from the tool from here or from here perpendicular to this. Okay. Now, if we take the perpendicular to this cutting edge NN and perpendicular to this cutting edge which is EE, all right, we will see these two views. So, in these two views, this is the rake face, all right, this is the rake face like this will be revealed here, and this is the rake face here, this is revealed here. As I said that just try to imagine that this is the cutting edge. Okay. So, rake face is not visible, it is inclined, either it is inclined like this or it is inclined more or it is inclined like this, it is not visible, but the face the cutting edge is visible. If you take the perpendicular to that, then only this inclination will be visible, you understand that. So, this inclination we are saying as the inclination which is of the rake face in here and in here. So, they are different, inclinations are different. Therefore, the angle which is between the rake face and the line perpendicular to the cutting velocity vector, it is here this line in this case and this line in the case of the NN, these two angles. One angle is called the normal rake angle and another is called the auxiliary normal, because this plane or this view is the auxiliary along the auxiliary normal plane, auxiliary cutting edge, okay, and this is normal. So, therefore, normal to the cutting edge. So, therefore, this plane is called the auxiliary normal cutting auxiliary normal plane, all right. This is called the normal plane because this is the cutting plane and perpendicular to the cutting plane will be the normal plane here, okay. Because this is perpendicular to the cutting edge particularly, that we have to mention. That is the difference, as I said, between the normal plane and the orthogonal plane. In this sequence, the angles are defined, that is inclination angle first, like in case of the ORS, then the normal orthogonal rake angle, principal normal flank angle. This actually should be normal orthogonal, this is not orthogonal, I am sorry, this is wrongly written here. This will be normal rake angle, this angle is the normal rake angle, okay. You can correct it. This is the principal normal flank angle, this is auxiliary normal flank angle, this is auxiliary cutting edge angle, this is principal cutting edge angle, and this is the nose radius, which is also given in millimeter because it is in the international system. So, exactly in this sequence the angles are defined, okay. And you have to read according to this sequence. If the first angle is given as let us say 1 degree or 0 degree, you cannot say that this angle is anything else but inclination angle, okay, and you have to read it in this sequence. Now, what happens is, suppose we purchase a tool in the coordinate system, okay, and we have to use it in the orthogonal rake system. Since the orthogonal rake system nomenclature is different than this coordinate system or the American system, ASA system, we have to convert these angles, okay, to our system. Now, this conversion is actually not very difficult. Here is the base plane, on the base plane the view is put here, okay. From here you will take a CC, like in the case of the ORS system, and the view is like this. Then we will take x and y, like in the coordinate system, xx we will put it in here and yy we will put it in here, okay. So, sorry, CC is we are putting it on the opposite side actually. This is the cutting, this is a view along the cutting plane CC. This view along the cutting plane we are putting in here. This is the YY section we are putting in here. This is the XX we are putting in here, and then there is another one which is perpendicular to this, that is OO, okay. OO we are putting it in here. Now, as you can see that in these 4 views that we have shown, or rather 5 views, this is one view that is in the base plane, we have combined the views of the orthogonal of the coordinate system, this is x and y, xx, yy, okay, and the orthogonal rake system, that is CC, and the here is the orthogonal, that is OO. So, now if we actually can project these points to the other views, then we can correlate through the simple geometry the angles. Let us take an example. Let us say tan of this angle, tan of this angle is this, okay, divided by this will be AC BC prime, okay. So, AC BC prime can be projected to this base, this thing as AB, all right, and BC BC prime can be projected to other views like this view, okay, like that we take a perpendicular here, put those points here, then you take a turn and perpendicular to this, project it in here, and then go perpendicular to this surface, go in here, and wherever it intersects it will be on this view. From this view, similarly, you put a mutually perpendicular two planes and project these points, and you can go to this view. So, you will see, if you carefully see this diagram, this conversion, by the way, this is geometry, plane geometry, and this can be found out from the reference books, from any textbooks, metal cutting textbooks, including some of the textbooks that have been referred, okay, for this particular course. Now, BC prime therefore can be said to be equal to Tx 2 prime, okay, this value, and this value is projected as the BC prime here. So, this same Tx 2 prime, okay, this can be as projected here as Ty 2 prime, like this, okay, in this here. So, this you can see. Similarly, all these, if you do that, in this case, finally what you can find out is that tan I, this is actually this relates to the sin gamma p, okay, tan alpha b. So, you can see that tan I, this is in the ORS system, sin gamma p, it is in the ORS system, that is the principal cutting edge angle, okay, principal cutting edge angle, you can see that it is in here, all right, gamma p, okay, and I angle is here, this is the tool inclination angle. So, this is into tan of alpha b is the back rake angle, okay, back rake angle is in the ASA system, this is the back rake angle, all right, this is in the ASA system, and minus cos gamma p and the tan alpha s, again this is ORS, alpha s is the side cutting edge side rake angle. So, this is also in the coordinate system. So, you can see that this equation actually relates the ORS system with the ASA system. Okay. So, therefore, if we have a tool in the ORS system or in ASA system, and you have to convert to other system like ASA or ORS, you can always do that using this kind of a simple geometrical equation. Now, equation which is obtained through simple geometry. Now, similarly, tan of this alpha O is here, this is the orthogonal rake angle, this can be found out from geometry as Q0 prime. Okay. So, this divided by this, and B0 Q0 prime can be projected to B0 Q0 BQ like in here. So, this is in the base plane and so on. So, like I have shown it here, finally, you can find out that the tan of the orthogonal rake angle is equal to sin of the principal cutting edge angle, tan of the side rake angle plus cos of the principal cutting edge angle and the tan of the back rake angle. So, here also the orthogonal system is related to the ASA system. So, either you have the ASA tool or the ORS tool, it can be converted to any other system. So, with each other. Now, this is the conversion from the ORS to ASA, because in one tool we have taken views of ORS and the ASA, okay, that is the coordinate system, and this is the orthogonal rake system. Similarly, we can actually convert the ORS system to NRS system, that is orthogonal rake system to the normal rake system. For that, there is an interesting phenomenon that we can actually do, because mostly it is the rake angle which is important. Okay. So, let us say that we will convert the rake angle, and how to convert that, and other angles will follow. All right. What is done is that we will take, since it is from ORS to NRS, so we will take a section in the orthogonal plane, along the orthogonal plane. So, along the orthogonal plane, let us say this is the hashed one. All right. So, therefore, the B0 Q0, this makes an angle with the line B0 x0 perpendicular to the cutting velocity vector, which will be orthogonal rake system, because this is the rake angle, this is the rake plane, and this will be then the orthogonal rake angle. All right. Now, what we do? So, therefore, similarly this angle will be the principal flank angle, because this is the angle in the Juarez system, flank angle in the Juarez system. So, then what we can do is that this is the axis x 0 z 0, this is the axis in which we are actually showing the orthogonal rake system, the view in the orthogonal rake system. That means, this is as if the sectional view along the orthogonal plane. With respect to x 0 z 0, particularly the z 0 axis, we will incline with an angle of I. Okay. When you do that, then the system on this, if we can project, it will be the normal rake system, okay, because this with an angle of I with respect to the orthogonal rake system, this will be the normal rake system. All right. And then these points we can project like this, that suppose this point, okay, we are projecting on the z n axis like that, and then we are coming back to the z 0 axis here. Okay. Then this point, if we connect with the edge of the tool, then the tool now that is given can be assumed safely as the sectional view of the normal rake system. Okay. So, therefore, this inclination or this face will be the rake face in the normal rake system, and the angle between the inclination of the rake face here and the line perpendicular to the cutting velocity vector, this angle will be a normal rake angle. So, once again, how we can convert this tool to a tool which is in the normal rake system? We are projecting this on the axis which is inclined to the z 0, z 0 is in the orthogonal rake by an angle of I, this is the inclination angle. So, then if this point is converted or projected to the orthogonal rake axis, that is the z 0, and then if we connect orthogonal rake point here with this point, so then this tool will be considered to be the tool in the normal rake system, and this angle will be then the normal rake angle, because this face will be the rake face in the normal rake system. All right. So, if we can do that, in this case you can find out these relationships, simple geometry, that gamma p, of course, I told you that this is 90 minus side cutting edge angle. Okay. Now, tan of this alpha n, this is equal to q 0 prime and the q n divided by q 0 prime and the b 0. All right. Then this is a simple geometry, and from here you can find out that this is cos I and this one is the tan of alpha 0 in the orthogonal rake system. So, therefore, altogether tan of the alpha n, which is in the normal rake system, this is equal to the cos of the I, okay, which is also in the normal rake system, as well as it is in the Juarez system, and the tan of the orthogonal rake. Okay. So, this actually equation relates the orthogonal rake system with the normal rake system. All right. So, as you understand, I once again tell you that this looks little complicated, but this is actually nothing but the in one view we have actually shown the projection or the sectional views and the projected views of both the systems, ORS and the NRS, ORS and the ASA. Okay. And then we are projecting points, edges from one view to the other views, and we are geometrically relating them. So, we are finding out the equation which will actually relate the two systems, angles of both systems. That is easy. Now, very important point is how to select the tool angles. All right. Meaning that we have now described the sets of in any of these systems, be it an ASA system or Juarez system or NRS system, we have basically the rake angles, flank angle and the 2 rake angles, 2 flank angles and 2 side cutting edge angles. Okay. So, how to select what is that value of the angle that you will be selecting, this is very important, and let us discuss on which factors the selection depends. Okay. With 0 inclination or back rake angle, that is I or the alpha b 0, the chip will flow parallel to the work surface and may cause removal problem. So, when this parallel to the workpiece surface, in that case it can further entangle with the workpiece or further entangle with the workpiece and the tool. Alright. It can cloud the machining zone. Suppose you are using any transducer, okay, any sensor that is non-contact. Using that sensor you are taking the signal with respect to the workpiece, for example, or with respect to the tool. Alright. In that case, that distance between the tool and the workpiece, if this place is filled up with the chip and it is not removed, that will give you wrong signal. Okay. But overall more dangerous is, even without any sensor, it actually can entangle, and entangling is always a problem. I told you when we discuss the continuous chip formation, that continuous chip formation is not desirable, because it will actually scratch the workpiece, it will scratch the tool and spoil the tool geometry, also the already machined surface. So, therefore, the 0 inclination angle or the back rake angle, the chip flow parallel to the workpiece surface and it will be difficult to remove. So, we have to have some kind of inclination angle, some inclination angle value or the back rake angle. Then the chip can be made to flow away from the workpiece and strike a suitable chip breaker. If you remember, I talked to you, I told you about the chip breaker, which is basically a protrusion on the rake face or a crater on the rake face, where the chip can actually be broken, so that the chip is not continuously flowing. So, we can have some value of the inclination angle or some value of the alpha b. So, right now we are talking qualitatively, not quantitatively. How much value, that we will discuss later. So, right now we are saying that there should be some kind of some angle, because inclination angle is 0, means it will actually problem with the chip flow. Okay. So, the chip in that case can be made to flow away from the workpiece and strike a suitable chip breaker, curl and break into small fragments. Okay. That is when you have some value of the work of the inclination angle and some value of the alpha b. Now, side rake, orthogonal rake and the normal rake angle, these angles influence the cutting forces, power and the surface finish. Okay. The larger is the rake angle, the lower are the cutting forces and power, and better is the surface. So, overall what we say is that suppose if we say that this along this axis we have the alpha. So, this alpha, as we said, is alpha 0 or side rake or normal rake, any one of them, all right. And if we say that this is the force, cutting force, so this will go like this, all right, meaning that as this value decreases, the force goes up, and vice versa, that as these increase, these values increase, the force goes down. Okay. So, why this happens, this I am going to discuss and I am going to explain it to you in my next discussion session. Thank you very much for your attention.